Hello students, now we will see the concept of monitors. So to avoid the semaphore problem in dining philosopher's problem where we saw that deadlocks can occur, we can use monitors as a solution to overcome deadlock problem in dining philosopher's problem. Okay, so in monitors, whatever you have seen, right, that is shared variables, they were all stored individually in the critical sections of each of the processes. So we will not store the shared variables in each of the processes. Instead, we have a module called as monitors, wherein we will be storing the shared variables. Okay, so here, only one process can may be active within the time at a monitor. That is, only one process will be allowed into a monitor. So the syntactic view of monitor is given like this. There is a construct monitor followed by the name of the monitor, and inside you will have shared variables, and there are procedures which will be used to access these shared variables. You can consider these shared variables as private, okay, and these procedures has public here. So these public procedures will be used to access the private shared variables. And remember, only one process will be allowed to enter into the monitor. And also you have an initialization code here. Yeah, now coming to schematic view of a monitor, here this is a monitor. You have a shared data here, and these are operations which are used to access this shared data. Along with operations, you will have initialization code. As you can see, only one process can enter into a critical into the monitor, and all the other processes that wants to gain entry into the monitor should be lined up in the queue. Next, here, so the monitor concepts allows us to maintain mutual exclusion. Along with mutual exclusion, they also provide synchronization. So synchronization is provided through condition variables. So this is the syntactic view of a declaring condition variables. You have a construct condition followed by the name of the condition variables. There are two operations that will be performed on a condition variable. One is x dot weight and one is x dot signal. Okay, so x dot weight, so this weight and signal is different from whatever you have seen earlier. Here weight represents a process that invokes the operation, that is a process that invokes wait operation is suspended. That is, a process that invokes wait operation on this condition variable x will be suspended, and the process that invokes signal operation on a condition variable x will be resumed. That is, the process that invokes x dot wait will be resumed whenever x dot signal is called. Okay. Now, so this is what I said to you. That is, you have a queue that will have the list of processes that are waiting to gain entry into the monitor. Okay. So these shared data. So we also store the condition variables in the shared data. So processes should actually first gain entry into the monitor, and after they gain into the monitor, in order to access the shared variable, here also they need to line up in the queue in order to share the shared variables, that is condition variables. Now we will provide a solution to dining philosopher's problem through monitors. Here we have the solution written, code written for dining philosopher's problem through monitors. So monitor is a construct and dining philosophers is a name given to the monitor. Here you have a enum structure. So it has three values, which is thinking, hungry and eating, and we have five philosophers. Okay, it's an area of five philosophers. So we have three values: thinking. A philosopher can be in a thinking state, or it can be in a hungry state, or he can be in an eating state. Okay, and we have a condition variable here called as self, and this is for the five philosophers. Clear? Okay, now let me now try to write the code 1 2 0 1 2 3 4. Okay, so here guys, you will see that initialization code is a code that has to be executed first. Okay, so initialization code will be executed first, right? So each of the processes starting from 0 to 4, initially they are in thinking state. Okay, so they are in thinking state. I'll be using the same to slide over the two slides. Okay, so this might be a little slow because I'll have to keep this data intact to hop in between the two slides. Okay, fine. Now, clear. Okay, so initially all the philosophers are in thinking state. Now, let's go to the previous slide. Okay, yes. Now, so if a philosopher, so philosophers are processes here, right? So if a philosopher wants to eat, then he should be hungry, right? So, and if he is hungry, he has to pick up his chopstick. Clear? So this pickup is to pick up the chopstick, and we are talking with respect to one of the philosophers. Let's consider I has to. That is, we are concentrating on this third philosopher, which is nothing but I is equal to 2. Okay, because we start from 0. So if he wants to eat, that means he is hungry, right? So we will change this T to H. That is, if he wants to eat, he should be hungry. And we will check or test if he can actually eat by going to test condition. Okay. Now let us go to test condition here. In test condition, it says that he can eat, that is the third philosopher, which is I is equal to 2 in our case, can eat only if his left philosopher is not eating and the philosopher sitting to his right is not eating and he himself is hungry. That is, his left philosopher should not be eating, his right philosopher should not be eating, and he himself should be hungry. Only then his state can be changed to eating state. That is, his state can be set to eating state, and after it is set to eating state, he can resume with his process of eating. That is, signal is resuming the process, so he can resume his process of eating. Clear? Yeah. Now let us assume that at the same time, let me erase this off. Okay, let me assume that at the same time P3, which is fourth process, okay, or the fourth philosopher. So fourth philosopher wants to eat. Okay, so if he wants to eat, that means he should be hungry, right? So this is I is equal to 3, so he should set its state value to hungry, and he will test if he can eat or not, right? Okay, so in that case, he should check if his left philosopher and his right philosopher are eating or not. So in that case, when he checks his left philosopher, and also this condition, guys, I plus 4 modulo 5 will give information about the left philosopher, and I plus 1 modulo 5 will give information about the right philosopher. As you can see, we will check for 3. So 3's left philosopher is 2, right? So what do you get here? 3 plus 4 is 7. So 7 divided by 5 is, that is modulo is 2. So 2 is the value of his left philosopher, and 3 plus 1, which is 4. So 4 modulo 5 is 4. So that is the value of the right philosopher. So what was I talking? If 3 wants to eat, then he wants to change, he has to change his state to hungry, and he should also check if his left philosopher and the right philosopher are eating or not. If they are eating, then if one of them is eating, then he obviously cannot eat because the left fork or the right fork is busy, right? So he will check if his left philosopher is eating. Yes, it is eating, so this condition fails because this is an AND operation, right? So if one of the condition fails, this entire condition fails, so he cannot eat. So that means what? If he is not able to eat, I'll just erase this, okay, so that you don't get confused. Okay, now that means if he is not able to eat, then his state is not going to be eating, right? So in that case, if his state is not going to eat, then he will block himself. So wait is a call that is a blocking call, right? That is the process that invokes this will be suspended. That means this one, that is the fourth philosopher, is going to suspend himself because he could not eat because his left fork was busy, or the left chopstick was busy with philosopher 3. Okay, so this is how it is done. Now let us assume that 2 wants to put down his fork using put down. Okay, so he, after he eats, he has to turn his eating state to thinking state, back to thinking state. So after he releases his chopsticks, he goes to thinking state, and now it is his job to allow his left philosopher or his right philosopher to eat. Okay, so that is what these two are test. So first he will test if the left philosopher wants to eat. So for example, this is 2, right? So 2 plus 4 is 6. So 6 more 5 is 1. So he will check for the second philosopher, and then he will check for the fourth philosopher. Okay, so let us check for the second philosopher. Okay, so I'll move on to the next slide here. Okay, so he will the second philosopher will check if he can eat or not. So now let the second philosopher check if his left philosopher is eating. Is he eating? No. Right? What about his right philosopher? Is he eating? No. Is he hungry? Yeah, so that is what I said. Sorry, I had to make this to H, because if he wants to eat, then he has to convert it into H. So his left philosopher is not eating, and his right philosopher is not eating, and he himself is hungry, right? So only in that case he can be eating, and then he can resume his process of eating. This is how, if you try to trace this particular code for each of the philosophers, you will find that at one or the other point of time, each one will be in a blocking state, but eventually it will get a chance to eat. So this is a very perfect solution to give a chance to each of the philosophers who can dine on the bowl of rice. Okay, so try tracing this particular code for all the processes or all the philosophers. You will find that each one gets its turn to eat from the bowl of rice. So this is a perfect solution to dining philosophers problem through the concept of monitors. That is, here you have some procedures. Those are test, pick up, drop the chopstick, and you have condition variables, which is self. Okay, so using these procedures, using the shared data, you can ensure that each philosopher gets a chance to dine. Thank you, guys.